This is the first screencast for Chapter 11 and Chapter 12. Chapter 12 is really short, so there's not a whole lot of content in there. It's mostly just some of the intermolecular forces with solids. But first, Chapter 11, in which we'll talk about intermolecular forces for liquids. So, looking at any particular temperature, you can say that a substance is a solid, a liquid, or a gas, and that is based upon the intermolecular forces and the strength that are holding these things together at any specific temperature. So this is a nice one to take a look at for the ones we have listed here. We have chlorine gas, and then bromine, and then iodine. And it's like, so what's the difference? They're all at the same temperature, but it's nice because we can see all three states listed here, and it has a lot to do with their intermolecular forces and how these things are attracted to each other. And we'll talk more about that individually as we're moving along. Okay, easy enough. We won't spend any time here. Just looking at things that are solids or liquids, that they're considered to be in a condensed state, which is much different than the gaseous state where the particles are really far apart. So some of the properties we can look at, you've done this in various classes, including your chemistry class from last year, just saying what are some of the differences or properties of a solid, liquid, or a gas. And you can look at those on your own. So some of the differences between the types of forces we mentioned, there's intermolecular forces, which is an attraction between two different particles. And then there's intramolecular forces, which is the attraction between the particles within whatever substance you happen to have. So intramolecular forces are always stronger than inter, otherwise it would break the particle apart and you would have something else. And we're seeing that listed right here. Same thing. I guess we can mention here that intramolecular forces help define what these substances are chemically, and then intermolecular forces help us establish what some of the physical properties are. So boiling point, melting points, vapor pressure, and such are things that are because of intermolecular forces. So they help establish, again, some of those physical properties. Some of these forces are called van der Waals forces, the intermolecular forces, and we'll see some of these listed on the next slide. So dipole-dipole interactions sounds a little bit more complicated than the others, but basically all you're talking about is particles have or may have a dipole. So a nice example of that typically is going to be HF, we'll go with that one, hydrogen fluoride or hydrofluoric acid. It has a dipole, so the electrons are pulled more so towards the fluorine. Therefore, it makes a negative side versus a positive side, and then you're going to have interaction amongst the particles in regards to attraction. So it's going to influence how this thing is put together. Hydrogen bonding, just to mention that one, is again the perfect example of that one is water, which is a very strong dipole, and usually you have to have nitrogen, oxygen, or fluorine within. And then London dispersion is just the kind of like everything has London dispersion, but it comes more into play when you have large particles with large mass, therefore large amounts of electrons, and then you have forces of attraction between the nuclei and the electrons that are floating around all these individual atoms. And we'll look at all these individually. And starting off, we'll do London dispersion. So a nice easy one is to look at small atoms that they don't have a lot going on. I believe this is helium, in which you have just a couple electrons, and there's not much else going on. There's not really a lot of attraction within it. There's no dipole, there's no hydrogen bonding. All it has is a couple of electrons. But under some really extreme conditions, you can get these things to attract to each other. So I think we're just kind of going to go through some of these slides, because I know there's a couple of them on here. Under some circumstances, the electrons may align themselves in a certain position, and then you would have attraction for the positive nuclei to it. So you would have the electrons moving to one side, Put these little guys here, and they're attracted to the nuclei, the positive nuclei. And then you get a shift of other electrons moving away. So if my electrons are located over here, my electrons in the other atom are going to repel to the other side. And you can look at this on your own. So one of the things they mention here in regards to a difference between dipole and London dispersion is they call it like an instantaneous dipole. The electrons are pushed in one, they're not normally pushed in any certain direction, but because of this close proximity of two atoms, you'll have this positive nuclei attracting the negative electrons, an instantaneous dipole, and then you get, of course, get a shift in the atom. So this is a couple good points to make here. Things that affect atoms having more dipole than another. And the ones we have listed here are a couple isomers of pentane. Pentane has 5 carbon atoms in a row. And we have 2 depictions of it. I'll just kind of draw these out. Is the top one here has more surface area. So you have 5 carbons in a row. So I have all this surface area on the outside, which is open for attraction to others. So again, the carbons imply you have these hydrogens, and then of course you have these electrons that are out there as well, so you have more potential for attraction. The other one on the bottom, the neopentane, you have 5 carbons as well, but I only have 3 carbons in a row, and then you have these 2 branches, 2,2-dimethylpropane. And that has less surface area, so it has less ability to have attraction. Think of like a drop of water. And this is not going to have as much attraction, and we see that expressed in the boiling point. So because this one here has more surface area, it has more potential for attraction, and it's going to have a higher boiling point than the neopentane. So there we go. So some other things we mentioned here is the point of this slide here is to show that these elements are right next to each other on the periodic table, neon and fluorine, but fluorine has a higher boiling point. I think that's what we're looking at here, higher boiling point than neon, because it has a higher molar mass, because there's 2 fluorines versus the 1 neon. So more electrons, more potential for attraction, higher boiling point. Okay, moving along to dipole-dipole. So there's a couple really good examples in the next few slides here. And what we see here is if you have a molecule that has a net negative side versus a net more positive side, these positive hydrogens floating over here versus the nitrogen in blue, you're going to have the potential for attraction between the negative nitrogen side. Remember, there's a pair of electrons kind of just hanging out here. This negative nitrogen being attracted to the positive hydrogen. So that's going to influence its ability to attract to itself. Another really good slide here is showing differences in boiling points. So take a look at the boiling points and notice how they all go up. And the molecules all look kind of similar. They're all this 3 chain here. So I'll kind of make an arrow to show the chain that we have in all of these. And the differences are kind of switching something out each time. So going from the first to second, they're switching out the carbon to a more electronegative oxygen sitting here. So it has more attraction to other probably hydrogens within the same mixture compound. So the melting point, boiling point is going to go up. And then we see the placement. We're moving the oxygen to an end position, which makes it much more, I don't know if it's a double bond or triple bond at the moment, but it has much more attraction to hydrogens again. And then the last position, changing out the oxygen to a much more exposed nitrogen again. So that is going to have more potential for attraction because it's more exposed. So again, the boiling point is going to go up. And we see this expressed in the dipole moment, which is this mu character here. And we see how that goes up. And again, we see the relationship to the boiling point. Okay? Well, this is a good place to end for the first lecture, and we'll move on to lecture number 2 after this.